We're going to continue exploring our shapes and things that with continuous charge distributions and the electric fields they create. So I'm going to start the same way I always start, is just reminding myself that when we're looking at electric fields, we're defining those in terms of Coulomb's law, the electrostatic constant, the charge creating the field, divided by the distance away that we're looking for that electric field. So here what I've drawn, hopefully drawn, it's going to be a ring of charge. So you could think in terms of like a nut, if you will, and it is charged, and therefore the charge is going to evenly disperse throughout the ring. And I want to know what the electric field is at this spot here. That's a distance a away from the center of the ring. So let's think in terms of our E and our KQ and what pieces we can pull out of that. And the first thing I look at, I'm like, okay, so R squared, the distance that I want is going to be something like this. Right, so I'm just making my right triangle there. And so that distance using Pythagorean, okay, that seems straightforward to me. I look at that, I'm like, okay, just square root of x squared plus a squared. So I feel like I've already gotten somewhere. So I can start off with that. That's going to give me KQ over the square root of x squared plus a squared, and that quantity squared. All right, I'm getting somewhere. Now, am I looking at something that's at an angle, or is it in a straight line? It's going to be at an angle. So I know that I'm going to have some sort of components here. Okay, and it's a continuous charge distribution. So what does that mean? I have this positive charge over here, and here is the point that I'm looking at. So for a positive charge, that means that this thing is going to continue on straight down. And that means that I'm going to have x and y components of that because it's at an angle. So I'm going to have like my x or y component coming down, something like that. I don't know if I made that long enough. And then coming over is my x component. Cool. So I'm definitely going to need to break this thing up. And because it's a continuous charge distribution, we're going to be looking at these pieces of electric field. So when you see this DE, that means that I'm going to be adding up all of the electric fields going completely around that ring in order to get all of my electric field charge, or electric field strength. Cool. So I feel like I'm getting somewhere. I need components, so before I run down a rabbit hole, the next thing I want to do is check for symmetry. So is there any symmetry to make life easier? And I look at this ring and I think, well, there's a charge up here, and I can draw a straight line down, and there's going to be a charge there. And that too is going to be the same distance away. So something like that. And I have an evenly distributed charge. So that means that the charges at top and bottom are going to be equal in magnitude and same in sign. So it's going to generate an electric field that is again going to repel away from, so kind of drawing a straight line through, more or less. So that's going to go give me an x component coming out like this, and a y component going up. So what I notice from this, and that should be only one-sided arrow, what I notice from this is because they are the same distance, same magnitude of charge, that my x and y pieces are going to be identical. And I look at this one, it's going in the opposite direction of this one, so I have one y vector going down, one going up. So what we're going to focus on then is just the x component. Now to make life easier, what I'm going to do is erase this piece so it's not so cluttered. And we'll focus on the top piece and take you out. I'm drawing a single arrow just because it's going to drive me nuts otherwise. Okay. And what do I notice from that? Well, what I notice is that this angle here is going to be the same as this angle here. And that for every one place, by symmetry, I'm going to have a second electric field. So I'm going to have a duplicate going on there. So I know that. And I'm going to want my DE in the X. All right. So my component that I want is going to be like DE. So let's go ahead and write that now. In the X, KQ over my R squared. So square root squared is just going to give me my X squared plus A squared. Times, let's see, X component, that's going to be some sort of cosine. Okay. Now I look at my Q. And I remind myself that we defined linear density in terms of this lambda thing. We said that lambda is the total electric charge of whatever surface we're looking at, that's the big Q, divided by its total length. Okay, so we're doing a circle here. So what are we going to end up with on a circle? We're going to look at something like this, right? Where I'm going to be looking at this arc length piece. So I'm going to have like this ds that's going to have in it some sort of dq. So my total lambda for this circle would be all of the q, and let's see, what would be the total length of a circle? Well, if I have a radius x, if I wanted to go for total, it would be 2 pi x. This would be for total. If I'm looking at d, or small pieces of that, let's see what I'm going to have. I'm going to have lambda equals dq times, or divided by this ds. ds. Cool, so I feel like I can rewrite my dE in terms of dq. So k, the pieces of q I'm adding up, going around the circle, divided by my r squared, which is this x squared plus a squared, cosine theta. All right. Now, instead of doing q's, because that's just kind of awkward, let's see if we can't rewrite this just like we did last time. So ds times lambda will equal my dq. It's a little easier to work with. We'll add that in there. We'll make a substitution for our dq. So I'll get dE in the x is going to equal k times lambda ds divided by x squared plus a squared cosine theta. All right, so our theta, we don't want that there because otherwise we have to do some sort of d theta, d phi, and that's ugly. So let's think about how we can define our theta. Well, our theta then, because that's that, and this is going to be the same. So remember, we have that guy coming down like that. So I know this side is A. My adjacent side, then I can say, so cosine of theta equals adjacent over hypotenuse equals adjacent is my A divided by my hypotenuse, which is the square root of x squared plus a squared. So we can rewrite this over here. I know what cosine theta is now. dEx equals k lambda ds over x squared plus a squared. Remember, that just comes from our r squared. Now times a divided by, let's write this as a fraction for the exponent, x squared plus a squared to the 1/2. And again, the just x squared plus a squared, that's just the same as x squared plus a squared raised to the 1. So 2 over 2 plus 1/2. We can rewrite this even nicer, that dE in the x equals k a lambda, just moving the a in, ds over x squared plus a squared to the 3/2. Beautiful. Feel like we're getting somewhere. Let's kind of page down a little bit. Now what can we do? Let's see. Let's go ahead and integrate. So I can integrate my dE to the x. And I can pull out all the constants. What's constants? The radius is constant, that's x. And a is the distance away, that's constant. So that the a and the denominator can all be pulled out, as can the lambda. So I'll have k a lambda divided by x squared plus a squared to the 3/2 times the integral of ds. And now let's think about what our units, our limits are going to be, rather, for our ds. It's my arc length going all the way around, so essentially the circumference. So if I'm going all the way around my circle, what am I going to get? I'm going to get this a up 0, sorry, starting at 0, to, let's see, what did we define our total arc length as? 2 pi x. Beautiful. So finally, let's pull this on up over here. We can evaluate this thing. So I'll get that my E total, so my E in the x is going to equal Ka lambda divided by x squared plus a squared to the 3/2. And s, so ds, there's no variable in there, so it just becomes s, evaluated at 0 to 2 pi x. Cool. So let's go ahead and evaluate this. Ka lambda divided by x squared plus a squared to the 3/2 times 2 pi x, starting at the upper limit and subtracting out the lower limit, which is just 0. Cool. So Ka lambda 2 pi x divided by x squared plus a squared to the 3/2. Now, if you look in your textbook, you will see something. There's our answer. That k equals 1 over, oh gosh, is it 2 pi or 4 pi? I can never remember. I think it's 4 pi. 4 pi epsilon naught. I'll post a correction if I'm wrong. So I can put this substitution into this to clean it up and make it look more like what we see in our textbooks. So I'll get Ke equals, whoops, not K, we're substituting in blue. E equals a lambda 2 pi x divided by 4 pi epsilon naught times x squared plus a squared to the 3/2. What's going to cancel out? Let's see. My pi is going to cancel. 2 is going to cancel and leave me with 2. And so I get a final expression of a equals a lambda x divided by, let's give myself a little more room, 2 epsilon naught times x squared plus a squared to the 3/2. And that's my final expression. Now, if I wanted to, if this needs to be in vector components, well, what I've determined is that this is all going to be in the x direction from how I've drawn it. I mean, I can look at it from other perspectives and essentially get, like, look below it and get in the y if I want. It doesn't much matter. You're still going to have, by symmetry, things canceling out. Okay? And let's double check. The one thing I didn't do, bad me, is label this, that I'm going to define to the right and up as positive. Therefore, the electric field is going to have a positive value. So let's just kind of go through this really quick and recap the logic, because we're just going to add a couple more shapes to think about and how to integrate. Is that we're always starting with this handy-dandy expression. And then what are we doing? We're looking at our distance away and then trying to come up with what our r squared is going to be. And then we need to think about what is changing. So when it was the line of charge, it was the dl or the dy, depending on what you wanted to label it. So we were working down the line of charge. And so we worked with this with dq versus dy. Now we're going in a circle, so I'm just looking at making that path around the circle. Or in terms of integration, when things are changing, that what I'm actually changing is that my ds, or my s rather, my arc length is defined in terms of 2 pi x, right, or 2 pi r. So we're just going to pull out those pieces that define the geometry of the object that we're looking at, and therefore the little chunks that we're adding up. And then the second really biggest thing is to look for symmetry, because if you have things that are cancel out top and bottom, you want that. That's going to make your life so much easier. And I don't know that I talked about this in the last one or this one. If I only wanted to do half of the circle, well, at the point that I've done things, all I need to do is change my limit of integration. All the other steps leading up to it are the same. So this is where, like, moving at an odder spot on the circle or only taking portion of it, that's where you would see that reflected.